You got all the experiences.
How's it going? Pretty good? Okay. What's that? Oh, can't access the slides? Really? Yeah. Okay. Let me fix that. I'll try at least. It says anyone can see them. They're not behaving. Maybe I put the wrong link. And is it not working still? It's not working. Is anyone else having difficulty finding the slides for today? Anyone else looking for the slides for today? Because no one mentioned this in Group A. Maybe they were just. Does anyone else have an issue if you go into Canvas and click on it? No one's checking the slides. Huh? Now it works? No one else cared. It's okay. Okay, welcome everybody. How are we doing? Good. All right, that's great. It's good to be back in person. Last week we were all virtual. Well, on Thursday, Group A was virtual for this, and that was interesting. And then I guess you were virtual for the lab. Hopefully, though, things are going okay. Any questions administratively? How are we doing? The post lab, okay. Ping pong or pickleball paddles galore. Okay. All right. Well, today we're going to continue our discussion on particle dynamics, focusing on intermolecular interactions. So we're going to move from particle dynamics to molecular dynamics. And we'll revisit the idea that we have particles in potential fields. So gravity has been our primary potential field of choice, and now we know how to handle a single particle as it goes through this potential field of gravity and as it interacts with walls. And today we're going to talk about what we do with a couple of particles and how we can model their interactions with each other. We'll cover the Lennard-Jones potential, and we'll also discuss how we can use base pairs, an approach to model a system that would have many particles. And of course, we'll do some simulations. Maybe not of course, but it's nice that we can bring some simulations into the class and show them. All right, now, any administrative questions now that we're here, we're settled? Next week, I'll be sending some information out about the group projects. As a reminder, you have groups of 3 that you'll be putting together, and you'll be looking at kind of creating a pre-proposal. And this will be a little bit tricky because we haven't done much with ANSYS, and pretty much almost all your projects will involve ANSYS. So, we'll be somewhat flexible. Projects can change over time, but there are many resources online available for that. There has been a little bit of a question in terms of when the office hours are. Okay, so the office hours are on the syllabi or syllabus for this semester, okay, not for the spring 2024 semester. Just putting it out there. And I don't know, Canvas does interesting things on that syllabus. There's like a syllabus tab on Canvas, and it populated it with a bunch of times that were not office hour times. Okay, so my office hours are on Tuesdays, so before class until about 1:30, so that I can get over here. And then I have office hours on Thursdays after class, 3:45 to 4:45. So it gives us a little bit of time to get to the office. And then the TAs, they have office hours on Mondays and Fridays. Again, this information is out there on the syllabus. There are actually kind of 2 very similar syllabi out there, one for Group A and one for Group B. And this is Group B, just putting it out there if you're interested in talking about things. Okay? We're here for you. We are. We try. Okay. Okay, well then let's keep going. So by the end of today, we're going to be able to kind of think about 2 questions or having some answers or some thoughts to different types of questions regarding the particle interactions and collisions we can model, and how do we do it? How do we do it in a simulation? Now, here's a question for some discussion. What types of mechanics might we employ to model interactions and collisions between particles? So up to this point, we focus mostly on just a single particle with a wall. What would be the mechanics though? How can you envision modeling a collision or other interactions between particles? So what are some ideas? What can you think about as some kind of underlying physics, some type of mechanics that would be useful for modeling their interactions? Yes, what? Did something happen? No, what?
It's like Newton's third law.
Huh?
Newton's third law.
Okay, so Newton's third law is a good one. All right. So that's kind of what's here, right? Okay. So that I agree. How may we have interactions in Newton's third law, though? Like, what are some options? We kind of discussed this previously a little bit, but what are some options? Yes?
Could you allow particles to exchange momentum?
Okay, so we could, yes. So you could come up with like a rule that says, we know how to hit, or we know how to handle walls. Well, we know how to handle these kinds of walls, right? And you could say, oh, now I just make like a spherical shell wall or a circular wall, and I'm going to attempt to use some of the same vector calculus to be able to say that is how we're going to conserve momentum. Okay, so that's one way. That's not how we're going to do it today, but that is one approach. That is one approach. Okay. Other ideas. So we have Newton's third law. Yes?
Use energy?
Okay, we can use energy, sure. Okay, that could be good for elastic collisions, right? Instead of at least if you could use it for inelastic collisions as well, but you probably want to use momentum instead, right? Because you're going to have, by definition with the inelastic ones, we're going to have some losses there. Okay, so say elastic collisions, energy would be okay. You could try a bunch of different things. The question, we could create a whole bunch of different rules and laws. Whether or not they make sense physically, we don't know, right? So we could do all kinds of things. Now, I remember one time, one of my kids, or someone was like, hey, billiard balls hit each other, or they get stuck. And I was like, oh, it's just conservation of energy. And I was wrong, because it needed to have conservation of momentum as well, right? Because they were getting stuck to each other. So anyway, we can make up all kinds of rules here. What else? How can we think of how they would interact with each other? So let's say the classic billiard ball example. If I say we're not going to define a wall, we need repulsion. We need repulsion, right? So what's a underlying physical principle that we could use to get some type of repulsion between two particles? What are some options? How could you think of repulsion? Yeah, so exactly, right? You could think, you could think, if I put a north pole and a north pole right on this side of the particle, on these sides of the particles, right, then I can get them to maybe, repel each other when they get closer, right? So they've got some momentum and they're coming closer and closer and closer, and then I get them to repel. Instead of using magnetics, what else could we use? Yeah, we could put them as charges, right? So you could have two particles with the same charge, and as they get very close to each other, right, they are going to develop a lot of repulsion. Okay, so these are the mechanisms you could use. We could use springs. Although springs are tricky, we talked a little bit about them. Springs, unless you cut them off, right, you're going to have your equilibrium, right? So you have springs between particles, and they could come to each other, and when they get really close, you can have them repel the particles. But then, of course, what happens is, they go into extension and they want to come back, right? So you could, if you cut them, if you define some law, right, you could cut them and then they could separate, and that would be more normal. Okay. So there are a lot of you can think of different physics, and we're going to introduce some intermolecular physics that you may not be familiar with. And I think we can credit Professor Singer again for this type of ideology, this type of work, especially with his background in material science. So he brings a different flavor to what we're talking about today. Okay, so we have already described gravity, and we can think of gravity as being always attractive. Okay, so the particles gravity will be great at getting them to want to get closer to each other. As we've seen though with geosynchronous orbits, those problems, if you have enough momentum, you can keep things cycling for a long period of time. So, and you can get them to slingshot off too, right? So maybe not exactly, what we would consider like bouncing particles, right? It's actually very much not exactly that, but you could think of trying to use gravity in that context. So when we have gravity, they're going to be attracted to each other. We mentioned springs, so we can think of the potential energy that is stored in the springs. We can think of there being a negative gradient of that potential energy, and that can lead to both attractive and repulsive forces. So you can think of the particles being connected in some way like this. And we talked about electrostatic charges a minute ago, so you can think of there being some type of potential field, and then we can think of them either having the same charge or opposite charges, and that dictating whether or not they're going to be attractive or repulsive. And if we have positive, they're going to be repulsive. If they're positive, negative, they'll be attractive. And we have, if you go back to some of your physics classes, you have Coulomb's law, and you can use this to be able to figure out what the force is given a distance between them. And then later today, we're going to talk about intermolecular forces. So we'll call these molecular pair potentials. And these are potential energy functions based on distance, which is similar to what you have in these other conservative systems. Okay, and in this case, these intermolecular forces are going to be things that we think about between atoms. So we want to think of them as electrons. Right, we can use the electrostatic approach. We want to think of them as molecules, and we want to attach some true physics to it. We can think about them in terms of potentials. So here's a question, though, as we're doing this. When we say, and we talked about this before, but in your words, what does it mean to use a potential function to figure out force? Right? Why are we talking about using potential functions? And you've already done this, right? You've done the Verlet, you've done the Euler now, you've done Verlet with walls. Just a reminder though, why do we care about the potential functions? Yes?
If you think of it like the area under a graph.
Okay, yeah.
So if you have the area, I guess like anti-differentiated.
Right, yeah, that's a good way to look at it. I'm glad you said that. So we're taking the negative gradient, right, which is essentially taking some derivative of these potential functions to figure out what the forces are. And what is interesting, at least, what is something that that is useful mathematically, or actually useful more engineering-wise about using these potential functions that are conservative, that are conservative. I'm kind of fishing, and I don't think I asked the question very well. What determines the forces generated by these potential functions? Do we care about position? Do we care about velocity? Do we care about acceleration? What determines the forces? Position. Who said that? Was that you, Rahman? No. Okay. Someone said position. Right? It's only position. And that may be a little bit counterintuitive, right? Because these things are going really fast, potentially, and they're zooming past each other, whatever. For these conservative fields, we only care about position for determining the force. But you have momentum that is being conserved, right? And you might have drag forces, like we've talked about, that could be dissipating energy from the system. Okay? But it's what's interesting, and we're going to hit on this a lot today, is that we are determining forces based on position. And Verlet does that, half position, whatever, half velocities, all the half steps, all that kind of stuff. Euler definitely does that as well for us. Okay, So, in pair potentials, all right, so this would be some type of description of a set of particles, and pair potentials are going to be looking at the interactions, paired interactions between a couple, right? A couple particles, right? We have a holiday coming up, whatever, or maybe it's not a holiday, but whatever it is, right? And we have lots of interactions. We have lots of excitement about couples. Okay, so these pair potentials, this is just that. You know, maybe you're thinking about the potential that you have with another individual around this time of the year. So, but it's the same kind of idea, right? And maybe it always attractive, and maybe it's not. Maybe your pair potential can change. You never know. Okay, maybe it needs work. So again, we're talking about having this kind of negative of the gradient in the potential function to give us the force. And the dynamics of the systems we're thinking about are definitely going to be determined by these pair potentials, okay, and the distances, and kind of where they were in the previous time step in terms of what their motion might have been and their velocity. And we also have to understand that if the trajectory of these particles is going to be altered in any way, the forces have to be significant relative to the masses. Right? I mean, yes, we're all pair potentials in this room, okay, in terms of gravity. But I'm not feeling much pull toward you, gravitationally speaking. Right? Because my mass is just, our masses are too large. So we have to make sure that we essentially decrease the mass sufficiently for there to be, or maybe not decrease, but we need the relative, right? The relative nature of these forces, because you can also, right, to get gravity to really happen, we actually use extremely large particles, right? We have systems of planets and solar systems and all kinds of things. Now, collisions. In our kind of orbital mechanics exercise, right? We had a position for the Earth, we had a changing position of the satellite, and we didn't really design it this way, but you could have said, hey, I'm going to give it just a little bit of velocity, and I'm going to have it go straight towards the Earth. And what would have happened in that case? If I said, okay, here's the Earth, here's the satellite, in that program that we wrote, what would have happened? It would have accelerated. So I give some initial velocity, right? It would have accelerated, yes. So it picked up a little bit of speed. And then what? When I got close, yes?
It was just oscillate back.
Yeah, it should just oscillate back and forth, right? Unless you prescribe a very high velocity and you send it out, way out there, and so then the potential field is, it's never going to really come back. Because it's got so much momentum. But you could design it, so that you kind of nicely get it so that it just goes back and forth. But there's no collision there, right? It's just it's cool, right? But there's not really any collision. And people who are designing trajectories for space vehicles, right? The Apollo missions and things. Wow, those were pretty cool, right? Right? They were definitely trying not to go straight at the moon. For multiple reasons. Okay, they had to approach it and get it into, and then get it out of that orbit. Slow down. So collisions, we can think of them in terms of gravity, but you're going to have trouble getting a repulsive balance. Okay, it's going to kind of go right through. Springs will be interesting, as we said before, but you can't really have them just bounce off and keep going. That's what you want. right? Because the springs will elongate and it'll pull the particles back to each other, pull back together, unless you were to kill or snip the spring. Electrostatic forces, yeah, this is gonna be fun, and this is what you're gonna do for the first lab. You're gonna focus on electrons, and you're focusing pretty much on electrons that have the same charge, and so they're going to want to repel each other. They want to go in opposite directions. And then we have these intermolecular forces, and the molecular interactions, needless to say, are complex, but we can, and these van der Waals interactions, they're complex because is it really just a particle and a particle? Well, no, because you got a nucleus and you've got electron orbits and all kinds of stuff. We'll talk a little bit more about our simplified models that we can use to describe their interactive behavior. Nonetheless, we can use these intermolecular forces to both be attractive and repulsive. So that's kind of fun. So if the particles are far enough from each other, they can be attractive to each other. But if they get in each other's way, they can definitely repel each other, right? And I think we can think of that from a human behavior as well. If it's siblings, if it's couples, whatever it is, right? You want to have some kind of, you can bond, but you don't really want to get in each other's space too much. Okay, now we also talked about this base pair approach to tracking particles at the very beginning, and what we're going to describe here is kind of two different approaches. So the first we're going to propose is kind of the approach we've been using, which has been very nice for one particle, but that's not the base pair approach. Okay. So what we do right now is we keep track of our single particle, right? What are we keeping track of? Keeping track of its position, velocity, and we know the acceleration is pretty much dictated by, we know that force is actually, if you have drag, right, you have dictated by velocity in the medium is traveling, and if it's got gravity acting, right, then you have to take the gravitational force divided by mass to figure out the acceleration. But we're keeping track of these kinds of things at this point. So if you had a satellite or a ball, and you're just one of them, you can keep track of the position, and we have the x's and the z's. Those are our containers. We have velocity vectors. The mass has not been changing much for us, but it could be changing, especially if it's a rocket that has some type of chemical reaction occurring, and it's dispensing off its fuel. And we can also think of the interactions if we had more than one particle in terms of their gravitational functions, all right? So one approach would be to scale up what we've been doing and say every one of our particles is an object. And, in today's world, right, we're not really supposed to think of other human beings as objects, right? You don't want to objectify another person, right? Nonetheless, this does kind of suggest for these particles that we can give them some, we give them some properties, like whatever those properties might be. Okay? So this is a nice approach, although it can be tedious when you start to have lots and lots of people, right? And so, I think it's amazing because you think of your kids, and if you have lots of kids, then you think, wow, this person has a lot of characteristics, and then this person has a lot of characteristics. So if you start to have a friend network, right? This person has a lot of characteristics. And before you know it, you're overloaded. So is there another way where we just keep track of the interactions but we look at the system a little bit more holistically, and we get back to the idea of the system is really made out of a bunch of interactive particles, and we just think of the base pairs, right? So, we're only interested in essentially how our particles interact with each other, not necessarily all the different attributes of every particle. That's maybe an oversimplification. So, if Jim is really far away from Michael, then maybe they don't interact too much, but Jane or Jill or Christina, whatever, right? They could, the quantities of their base pair interactions could be larger based on their proximity, for example. I don't know, these are pretty bad analogies that I haven't thought through so carefully. Okay, so what we're going to do is we're going to think about a non-object oriented approach, and this is not like object oriented programming. Okay, this is a bunch of particles in a system, and what we can do is come up with some column vectors that describe the attributes of the whole system. So this X column vector, what do you think this X is telling us? I'll give you a hint. What do you think the X is now telling us? Sure, yes, Neil.
Positions of our particles.
Yeah, this X is telling you the X position, right? It's telling you a story. Never mind. Okay, it's telling, remember the X position, the right, whatever. Okay, so the climax, all that stuff. It's the X position of all the particles in the system. The Y similarly shows you all the Y positions, and the Z shows you all the Z positions. Okay, now what is the length? Well, the length of these column vectors is going to be the number of particles that you have in your system. Similarly, we can keep track of the velocities this way. So we have U for the X velocities, V for the Y velocities, and Z for the W. What comes U, V, not Z? U, V, W. That's how the alphabet works. Okay? And now what we need are to think about interactives and interactions between them. And this is where it starts to get just maybe a little bit more complicated. So, and also we want to think about unique base pair interactions. So you can think, okay, there's base pair, they're already, each pair is going to interact with each other. It's going to have different magnitude depending on where they are relative to each other. And I don't want to double count, right? So like, if I've calculated the force that particle B exerts on particle A, and I'm using the third law, as someone pointed out, right? Then I can know what the particle A exerts on B. Boom, I put it in one time, unique in that sense, right? And also unique in particle A doesn't exert a force on particle A. Okay? That may sound kind of silly, but that's something also that you want to keep track of when you're doing the accounting. So, here we go with your unique base pair interactions. F of X, so this would be now the forces in the X directions, okay, and it starts off what looks like a column vector, all right, but we're going to build it up. We're going to build it up, going to build it up, build it up. So this actually becomes a matrix, okay, and I'll draw a little bit more on this in a second, but if you look at the first column vector for fx11, fx22, fx33, what are you going to put in that vector? If you think of the subscript 1 exerts something on 1. Yes? 0. So that whole vector is going to be 0. Okay? But that we keep it there because it's going to be part of this matrix. Okay? And then the next column, right, would be this fx12 minus fx12, and then zeros the rest of the way down. Okay? So this is saying, I'm going to keep track of how particle 1 interacts with particle 2, and then I'm going to have an equal and opposite force that describes the inverse reaction. And then I do the same thing over here with fx13 and minus fx13. Okay, so that's how 1 and 3 interact with each other. And then 2 and 3 can interact with each other. 2 and 4 can interact with each other. And so we keep track of all these interactions. And you can kind of see that we're not going to keep track of these like the 2, 1. Like we're not going to have like a positive fx sub 2, 1, right? But in the end, okay, so we have kind of like this matrix that we're forming that we're going to work with, but in the end, what we have is just one column vector. And that might be a little counterintuitive the way I describe it. But you just have one column vector where the first component of that column vector, so that like the fx, we'll call it 1, which would have the summation of all the other particles interacting with it, right? That one is going to be like fx11 plus fx12 plus fx13, right? So how are 2, how are 3, how are 4, how are 5, however many particles, how are they, what's the net force, right? The resultant force on particle 1, okay, in the x direction. So we also have an Fy, and we also have an Fc, and they're not rewritten. Any questions on what we're describing? On this kind of base pair, non-object-oriented approach. Any insights that you think I should have said that I didn't, that you would like to share? So I have a question in terms of how would you implement this? Because we got a simulator, right? So how do you implement it? Yes, double for loop. Okay, so we can use a double for loop. Did you look at the slides? No. Okay, so double for loop. All right. So what do you want to iterate through? What do you want to go through?
You go through every particle, and then for every particle, go through every other particle, and calculate all the forces on that particle, on the original particle.
Yes.
And then like have one.
Yeah, exactly. Right. That's very well said. Okay. So we're gonna be marching along using some type of method. Euler method would work. Related integration method would work. Okay, and where is it that we want to calculate all these interactions? Well, we want to calculate them when we had to derive the acceleration, right? That's when we really care about this. The velocity, the position, yeah, we got to update that, but we've got to update the acceleration so that we can update velocity, and then we can update that. So, and then you have this. We have to derive it here, and that will allow us to do these other calculations. So here's the double for loop, like you said. Okay, we can think of having an I subscript and a J subscript. Okay, and for I, yeah, we're going to want to go through every single particle. Okay, we want to go through all the particles in the I. And then for the J, these are unique base pairs. Okay, so for J, we're just going through like this I plus 1 to n. All right. So we're going to go through all of them again, and then when we get to these, when we decide whether or not we have an interaction, we have to check: is this a unique base pair or not? And one way to check to see if it's a unique base pair is to create this unique base pair matrix. Okay? So this is where you have a 0 on the main diagonal because particle 1 doesn't interact with itself in a meaningful way in terms of calculating a force. Particle 2 doesn't interact with itself in a meaningful way, right? Particle 3 doesn't interact with itself in a meaningful way, okay? And I don't want to double count. Once I've calculated how particle 1 and particle 2 interact with each other, when I get down to here, I don't want to calculate that interaction either, okay? But I also have a way to like make sure that I don't waste my time and go through this entire matrix. Okay? And what's in here? This is just looking at calculating out, all right, distances, calculating out the forces, and creating this matrix, or creating this essentially this vector for the x direction and the vector for the y direction. And this would be inside Verlet, right? So this is just to calculate the forces, and in this case we're doing Coulomb forces, right? And this is electrostatics. Any questions on this? So maybe a little bit counterintuitive because we have to keep track of all this stuff, but it's a nice way to you know, you're like, well, we really shouldn't be using for loops because for loops are inefficient. True. Okay. Not going to necessarily deny that. Okay. There might be a better way to do that, especially if you know the size of the matrix already. You can try to like speed up. But for our intents and purposes, and for the visualization, in terms of being able to do this work, this is how we're going about it. Questions, comments? All right. Yes.
Would it be better to do this in spherical coordinates?
Okay, so we're doing 2D problems. We're doing 2D problems here. Okay? So you could imagine, yeah, I mean, you could do this in polar coordinates instead if you wanted. But that can be tricky if, I mean, we are thinking about two and multiple particles interacting with each other. Everything is not kind of about the origin. Right? So often polar coordinates or spherical coordinates are kind of nice when you're in the spot. But so like, you know, like for example, if you have the Earth with a satellite, I think polar coordinates, that's a nice, or spherical coordinates even, that would be like a nice way to go. Because assuming that the Earth is kind of at the origin of that system. But if you're thinking about how all the planets in the solar system are going around and interacting with each other weekly, all right, about the sun, again, well, if the sun is your center, that's probably not bad. You can keep track of everything. But then if you start thinking about the sun in a galaxy, I guess if you know where the center of a galaxy, the theoretical center of a galaxy is, then maybe, but that's probably a case where you're stuck doing Cartesian coordinates. Good question, good insight, thank you. Any other thoughts? Okay. So let's talk about some demos. This is fun. All right. So this is what you're going to do in the lab, and it's going to highlight a few important principles. Remember, we've talked about discretization. What are we discretizing in this example? In these examples, what are we discretizing? When we did bouncing balls, when we did particle geosynchronous orbits, what are we discretizing? Time, yes, right? Yes, time. Are we discretizing geometry yet? Not really, right? Geometry is free. All right? That's very nice. Okay, so we're still just discretizing time. And so these are not MATLAB demos, obviously. I'm going to get to them, right? But you can imagine, like, if you have a particle and you have another particle, and the particle 1 is coming. That's a really bad color to choose. Okay, well, it's not that bad. You can kind of see it. But, you know, particle 1 has some velocity and is coming and it's going to, you know, interact with particle number 2. And we're going to say this is Coulomb. Oh, now that's a bad idea. Okay. Okay. Okay, with like with charges of the same sign. Okay, so this particle can come. Oh no. Okay, yeah. So this, where did it go? Oh, there it is. Okay, so this particle can come, right? And it can interact with this particle over here. And if they're the same sign, that means that we should get a repulsion. Okay. So what is Verlet doing? It's keeping track, right? It's going to say, oh, the particle is there, right? And then it's going to be here, and then it's going to be here. You know, they're going to get closer and closer, right? And then what's going to happen? Well, that negative gradient of the potential between them is going to go through the roof because they're going to be really close to each other, right? We have that over R term. And so when that distance gets very small, then they're going to repel each other. Now, what happens when a billiard ball hits another billiard ball? And let's say no spin, head-on collision. What is the behavior that you expect? Anyone play the pool? I'm a horrible pool player. Yes?
The first ball stops and then the ball gets like transferred in the same direction.
Exactly, right? We've been talking about this. So what we expect when they finally touch, right? You're going to see that this particle will take the position, the left particle will take the position of the right particle, and this particle is going to shoot off. Okay, that's the behavior you want. What happens if they're not head on? Like what happens if you purposely go to the side of center? Yeah?
You gotta treat it like a momentum problem with two balls, like with angles.
Yeah.
You have to be conservative.
Yeah, so this is the head-on collision. And it's elastic. I'm going to say that, right? That's not, don't try this when you drive home today or something, right? With another car. Oh yeah, but the guy in the class said that we would just bounce off each other. No. All right. So if you raise each other, right? Let's say you're a little bit offset, but the particle is coming this direction, right? Then what happens is this particle is this direction, right? And this particle is going to go like off that direction. Okay? So we're going to play billiards today. That's what we're going to do. Now, what good or bad could happen with our discretization? Remember, we're discretizing time. So what could happen? What happens if you use a very small time step? Does anything bad happen if you use a very small time step? Just slow, right? You could be really slow. So this simulation, right? It will run with a very slow time step, but you could be there until you graduate, and you'd still be on assignment number 3. That would be sad. Okay. What if you use a very large time step? Yeah.
Well, how are you defining like interaction? Is it like if one ball have to be within the vicinity of the other one?
The beautiful thing is we actually let the math do the work for us. Okay? Because every time step, we are calculating the forces between the two particles. Right? But that forcing function doesn't become significant relative to the velocities that we pick and the masses that we pick until they're within a certain distance of each other. Does that make sense? So the math completely dictates this. Okay? We're going to use the mass of electrons and we're going to use the charges, and we're going to use Coulomb's law.
With the large times table, you just have one kind of.
Right, it'll just jump, it'll go right through the other one. Okay? It's that problem again. And this time it's not so much a problem what gravity does with initial velocity, right? Through another object, it'll just keep going through it, right? This is a problem of we miss that window of opportunity for there to be repulsion, and it just goes through. They still interact, they're still interacting forces, it just doesn't have a significant outcome. All right, so, let's do it. I'm going to try. Okay, so here is the code that you'll get to write in the lab. And in this case, we have just two particles, and we have the charges being assigned some negative value. Okay, that's the charge of an electron in coulombs. We have the mass of an electron, and then this cell is just, these are not cells. This is just kind of the field of view that we're looking at. Okay, this is the, even though we're not discretizing space at this point, this is just, I gotta pick a window to look at, and I'm looking at it. Okay, we're looking at it. Now, these are the x positions, these are the y positions. Now, right now it's set so that x is at minus 3 millimeters. Do you see that? And for particle 1, these are actually column vectors. The apostrophe is the transpose, right? So we have one particle is at minus 3. That's going to be the one on the left. The other particle is at 0. Okay? And then if you look at the y, right now I have that second particle actually offset a little bit down. Okay? But let's do the first example. Let's put it up. So they're just head-on collision. Not super exciting, but let's do it. And minus 9, that means nanometers. Okay, so we're really pretty far. The initial velocity, I guess I kind of skipped that, but the initial velocity is also prescribed. Boom. All right, so what do you see there? How did you describe, what was your name over here in the jacket?
Rishi.
Huh?
Rishi.
So is this what you expect based on what you said a minute ago? You want to see it again?
Yeah.
Yeah, okay. So I kind of caught you off guard. All right, so this is head-on collision, elastic collision. Is this what you expect?
Yeah.
Yeah, you're right, it is. Boom. All right, good, right? That's what we expect. You're like, wait, are you trying to trick me? No, I'm not trying to trick you. That's what you expect. That blue particle, right, what happens? It kind of just comes to a stop, and the red particle then keeps going, right? And right now, we have hold on, so we have we're in the drawing. Where is this? Right. So right now, if we just comment that out, actually, which one is it? Yeah, it should be, if we comment both of these out. Oops. Okay. Oops. Yeah, okay. Okay, so, all right, I got rid of too many holes. So that's like the ghost, that's the invisible man. That's the invisible particle hitting the other one. All right, sorry. Okay. Yeah, so we can get this, we'll put it back on. Okay, but the point is you don't have to have that keeping track of the field. Okay, now, what happens if we mess with time? All right, so right now it's at 0.1 picoseconds. What happens if we do like a factor of 10? Will anything happen? Well, our simulation should run faster, right? Do we still get the behavior we want? Yeah, more or less, we're still getting the behavior. All right, factor of 10 faster. What happens if we do another factor of 10? Okay. Going fast? Oh, what happened there? All right, you see they're interacting, but it jumped over to the other side of the particle, and then it started to repel it to go backward. All right? So once again, we see the necessity of getting the time step right. How would we know when we got the right time step? Someone else. How would we know? Yes, Isha. Right. That's one way, and that's right. All right. So we get the behavior matching what we think, and also, if we're not sure what the behavior is, as we decrease the time step, the behavior doesn't change. Right. So like here, if I had a too large of a time step initially, I'm like, well, one, I can see that's not what I expected, and then I have to decrease, and then I start to see what I expect, and then I decrease and decrease a little bit more. Nothing is changing. I've got good enough time step. That's convergence. That is convergence. Okay. So let's go ahead and we'll put it back. It was at 1. That's pretty fast, or a pretty tiny time step. Okay. And now what we'll do is we're going to put back in this this offset. Okay. So it was pretty small. Let's say, oh, that's not where it is. That's the velocity. You could do that too, but let's just say we're going to put them off by like 10 nanometers in the vertical direction. That's pretty small. Okay. And remember, these are point particles. They don't really have this, they're not really colliding with each other. And what do we see? Is that what you said? Is that what you expect, Rishi?
Yeah.
Yeah, that's what you expect, right? And that one particle goes off, and there's even the calculation of what the angle between the two in degrees will be. So if you look at the bottom code, and again, when you do the tutorial, you'll see how to calculate all these things out, and you'll be able to get each line of the code. What are we using to calculate the angle? Just look at that code. Tell me what is the code doing there to figure out the angle. Right? I mean, you can see the angle, right? It looks like it's pretty close to 90 degrees. How do we calculate that?
You're just taking the arc, like the inverse cosine of the two velocity vectors.
Right. Okay. So you've got exactly right. So you're looking at the velocity vectors, first of all, right? So even though we saw like these nice plots, right, and we can see that the positions form nice orthogonal lines or close to orthogonal lines, right? We're looking at the velocity, and that's the result of the velocity doing what it's doing. So we're looking at the velocity vectors. Does that mean that we need to be right at the vertex where these particles hit each other? No, right? What we're doing is we're taking the last. This code is running through, and this is the final, this is the final hurrah. However long we're running it, right? These are the velocity vectors that we've gotten after these particles. This is not just where they hit each other, right? This is later. And then we can figure out, okay, there's one velocity vector, here's another velocity vector, and I can figure out, using the dot product, right? I can figure out what the projection would be, and I can figure out what the angle is going to be using the arc cosine there. Okay, because A dot B is going to be equal to AB cosine theta. Okay. And we can do that with the unit vectors, right? So we actually created unit vectors to do that, so it's not dependent on the actual velocity, right? Because that makes sense too. Okay. So we don't have to divide by the magnitude later when we do the inverse arc cosine, the arc cosine. Okay. Any questions? Fun? All right. So so you'll get a chance to play with this a little bit. If you want, you can also play with multiple electrons interacting with each other. Let's see if this still works. So in this case, we've got 3 electrons, and then that one hits that one, and then this one doesn't have a head-on collision, but it has, at an angle, and then it sends the other one. All right. So this is kind of the fun stuff to do in the lab. Let's now do something that's still fun, but a little bit more painful. So intermolecular interactions. A little bit of a spoiler alert. Unlike what we've been talking about up to this point, where these fields are either, except for the springs, but we tossed them out, where the fields are going to lead to solely attractive or solely repulsive forces. We can think of these intermolecular interactions with these specific scalar potentials as giving us both attractive and repulsive behavior. And we've kind of already talked about this, right? We talked about how if you get into your space, someone's space, they have every right to push you away. Okay, so let's think first about two particles far apart from each other. And then they get to a certain distance and they can feel each other. They're attracted to each other, kind of like gravity. And actually, you'll see in a minute that the scalar potential function actually looks kind of like gravity, scalar potential function, when at this distance. Then, that attractive force brings them very close to each other, and as they get closer and closer, they start to not like that. All right, and I guess in the realm of hand waving of molecular dynamics, the electron clouds, they begin to overlap with each other, and that's really not fun, unless you're doing a covalent bond type thing. Okay? So you have these like van der Waals interactions that are kind of pulling them to each other, and then that they want to be repelled from each other once they get in each other's space. So John Lennard-Jones is the person responsible for simplifying the modeling, or coming up with one model that simplifies all this behavior. And this is modeling the attractive van der Waals forces in noble gases, and then describing what happens when they get too close to each other. Okay, so look. This right here is the overall, this curve 1 is kind of what looks like what we call the kind of general, that's like the Lennard-Jones potential. You'll see that in a minute. But it's like a combination of different things being added to each other. For example, this function, this number 2 function, if it were below, this should look a little bit familiar. Remember well, maybe you don't remember because I wouldn't remember. We were talking about gravity. Oh, what just happened? Okay, so we're talking about gravity, potential, and we went through it pretty fast, but this is kind of what gravity looks like. Okay. And this x-axis, so this is the potential, is the y-axis, so this is u here, and then we can say this is some type of r, distance between two particles. Okay. So the negative gradient of this is always going to be, well, this has positive slope. All these have positive slope, right? At least if I'm on the right side. Everything has positive slope, so then negative of the gradient, right? That would mean negative. So negative slope the entire time, or negative the slope is negative. So negative gradient is negative the whole time. Okay, does that make sense? So that means it's, in this case, it's always attractive. It's always attractive. So out here, like if you're underneath as well, the 0 line, okay, this is always attractive. It's always, well, it's attractive until you kind of get to a certain point. At this inflection point, once you get to this distance, then the slope flipped. The negative gradient flips, and that becomes extremely repulsive. repulsive. The negative gradient would be positive, and that becomes the opposite direction. And of course, we can argue the signs and everything that you have here, but you see that the slope changes sign once it's gone through this inflection. And it's in both cases, right? When you get close to each other, the gravity goes way up. The gravitational force can go way up. Okay. And in the Lennard-Jones potential, the repulsive force can go way up because the slope goes way up. Okay. This gravitational potential function, I mean, it's a little bit tricky, but this is kind of like a black hole or something, right? Where something's getting sucked. Now, or between two very large masses that get close to each other. That's another way to look at it. Okay, so a little bit more on this. So the Lennard-Jones potential has a couple parameters that we use to describe it. One is this epsilon, okay, which is the well depth, and this is kind of a measure of how strongly the two particles are attracted to each other. And this sigma is the distance at which the intermolecular potential between the two particles is 0. That's fine. And then we have something that's called this internuclear distance, okay? And this internuclear distance, this r is it's like the 6th root of 2 times sigma, right? I guess I should have pointed out that this is the potential that Lennard-Jones came up with. Okay? And it's called like a 12-6 potential. It has this 12th power and a 6th power relationship. Right? And it's pretty wild, right? You're like, whoa, these are, when you take derivatives of something to the 12th, right? That's a pretty significant coefficient that it adds to the situation. 6th as well, right? But this is what these functions look like. And this is kind of an empirical approach to fitting to interactions of the day. Okay, so let's talk about this a little bit more. So this Lennard-Jones potential has its minimum at this distance, r min. Sorry, did I draw it? Yeah, I drew it to the right spot. So right there at where the well is. So this r min, rm, and this is where you have this 2 to the 1/6 times the sigma. This graph is the same, but it's just been kind of normalized by the epsilon over here, and it's been normalized by the sigma on the x-axis. So it's sharing the same information. And the force associated with the Lennard-Jones potential can be thought of as the negative gradient, right? So if you take the negative gradient here, right, this is the derivative, this is where you get these very large exponents, okay? Very large coefficients, and more importantly, you get these, this r to the 13th and r to the 7th, or the inverse of that, right? So if you get all the distances right, what we're saying here is that the derivatives can be extremely volatile, essentially. Okay, not different from the stock market. If you have a lot of derivatives, okay, that's another bad analogy. Okay, but the derivatives are more volatile than the actual things that you're tracking. Not that I or anyone else really knows how to predict what the stock market is going to do. Okay, but derivatives are volatile. Okay. Now here, this is the KB, K sub B. That's the Boltzmann constant. So you probably don't care that much about all this stuff. But the epsilon over the Boltzmann constant is 120 for argon. This is right. This is a gas that we can model. And then in that case, we have this sigma, which is equal to 0.34 nanometers. And then the intermolecular distance ends up being something like 0.44 nanometers, or like 44 angstroms or so. So that, over here, this is about, so this intermolecular distance, this is like something like 44, or 0.44 nanometers, all right, or 44 angstroms, or 4.4 angstroms, okay? And this is the force that you generate between these atoms. Any questions on what we've covered so far? Any questions? So how do we determine the force between atoms or molecules if we're using this model? Solely on position. Right? That is the power of using a conservative scalar potential. Dynamics? Well, they're based on position and the velocities of the particles at a given moment in time. And that will help model what happens in the next moment in time. So, what is your mission for this? Okay, and here's like you'll see that there's this pair potential function, right, that you can create to create a force. What is your mission if we choose to accept it? Well, our mission is going to be able to accurately model the interaction between just two atoms. Right, so keep in mind that the lab is modeling the repulsive interactions between what? Two electrons. And now we're dealing with atoms. There's a lot more weight involved here, a lot more mass, better said. Okay, a lot more mass. Okay, so what we're going to attempt, okay, to do is to see, can we get them to bounce off of each other? What is the recipe for getting them to bounce off each other? And I'm not going to run the particular simulation I have up. I don't think this is not a bouncing one. I don't think. Is it a bouncing one? No, this is not a bouncing one. Or it's okay. Sorry. It's a bouncing one in a different sense. Okay. What are the conditions to get like a billiard ball jumping, like propulsion type behavior? What would you have to do? Just think not in terms of the code, just in terms of the physics. I have atom 1, atom 2, and I want it to behave like a billiard ball, even though I have this dangerously volatile Lennard-Jones potential describing the force between them. What do you do? Yes, Rishi? Yeah.
You could first calculate the initial momentum involved, or whatever, and then as it collides with something, it sort of gets transferred. Another calculation happens so that you get the final momentum of the two balls involved.
Okay. Yeah. That could be one way to do it. Okay. That could be one way. All right. That's in terms of the calculation. If I want it to behave like a billiard ball type system, what do I do? Yes, Rohan.
Should we really fast?
Yeah, you go ahead and put a lot of initial momentum on that first billiard ball, and you get it to bang, hit that one, and boom, it's gone. All right, so that you don't get trapped. It's like, there's so many analogies here. Life has many vices. Many times it's good to just look away, run. Okay, you just run. Right? And if you read the Bible, there's stories of this. Right? But anyway, so you just like people who didn't got in trouble. Right? David, if you want the story of David, all right, that's a good example. So if David had just hit it and bolted, a lot of things would have been different. All right. So that's one approach here. Okay. Now, what if I want them to be with each other forever? What do I do there? What do do you do? What do you do there?
Make it slow.
Yeah, take it slow, right? It's like, hey, you know, yeah, all that wonderful vice looks pretty good. I think I'm gonna hang around for a little while. Okay, whatever it might be. And so, yeah, you can get a situation where the particles are, quote, bonded with each other. Now, here's the thing. In our simulation, what you're going to see is bonding. So this I just realized why bouncing is a bad word for this. Because if I hit it really hard, I can get it to be repelled and take off. All right? And that's kind of like bouncing. That's what bouncing is. When I mean bouncing here, what I mean is that they bounce and then they come back. So it's like, anyone got a better word for that? Yeah, they're oscillating. That's good. They're oscillating, right? And they can keep traveling along together. Okay, that's fine. But they're like now they can't be separated easily. Okay, and so that is what happens with molecules, right? Atoms, right? Like in this any material that we have all these networks of vibrating atoms that are just like hanging out with each other. They're not touching each other, right? But they're like sticking with each other, right? So when we talk about bouncing, in this case, we're talking about this oscillating behavior. I think now that's why this was so confusing for the last semester. I said, yeah, they're just bouncing. No. I should have said they're oscillating bouncing. Okay? So what does that look like? I think if I got this right, I had to go into the post-lab assignment. Okay. Right? Make sure you're in the right directory. I don't recommend using the path. Okay, so now that looks very similar. Ooh, they're attracted. See that? They're bouncing really nicely off of each other. Like that. And they still have some of that momentum, right, from when the particle, because that particle, the blue particle, came from the left, right, and it wanted to go to the right. So now they're bouncing off of each other, and they're still kind of moving. They're still moving to the right, very nicely. Okay. So you've got to get them to go slow. Now, what could mess this behavior up? See this? These are the X positions, right? It's so nice. It's a beautiful thing. They're just like oscillating with each other. And it's cool, right? The physics are determining this. But I said you have to set, and Professor Singer said, give credit where credit is due, right? Set up this problem so we had all these nice behaviors that are visible. Okay. What is a problem, though, if I don't have the right time step? And this is the last thing I want to talk about. Okay. So you see these, I blew past this, right? If I have a small time step and I'm marching along, right? That's my time step. I can't go too far up, right? Then I can just kind of go back or whatever if I'm going very slowly, right? Time step is relative. It's really relative to how fast things are moving, right? If I have really slow movement, then I can have a very large time step, right? So there's this balance. There's this balance between time step and velocity. But if my time step is large and it doesn't capture, I do like this. And suddenly, the next time I'm like up here, right? That can cause an adverse reaction. Okay? It could cause a highly repulsive force, or it could cause the particle, once it's already gone past, to if it goes through it and then it's like got that lot of repulsive stuff, it'll cause them to shoot off, right? Kind of like what we saw with the large time step for gravity, right? or cause them to like be attracted then shoot off. That can happen too. Okay, all kinds of cool stuff that can happen. So there are two things that you would have to get right for this problem to work in the post lab. One is you go nice and slow. All right, as you want to bring those things into each other and you want them to interact. But then two, make sure your time step is small enough so that you, well, one, okay, make sure it's small enough so that you actually capture the Lennard-Jones potential appropriately. Okay? That's it. Any questions? This is kind of a fun lab. It is. You can see bouncing balls. I mean, who doesn't like, I mean, we watch basketball, we watch all kinds of sports, pickleball, right? Football. I don't know, we haven't done a football problem. Maybe we could do a football problem. Now's a good time for football, I guess, if you're an Eagles fan, right? Okay, so let's do the attendance, and then we'll be off on our merry way. Thank you, everybody. Oh, come on. I went through all, oh, good. I went through all the effort to make it work this time. Okay.